Assuming this model, let's answer the following question. If we find 20% of the words in Milton's poem to be unusual, then what fraction of Chaucer's poetry did Shakespeare's audience recognize? Ooh, that sounds difficult. What can we do with that? Well, let's say that t corresponds to the year. We're going to be interested in two functions of t. The first, w sub m, is the number of words in Milton's usage currently used at time t. That is, according to the solution to this differential equation, w sub m at 1667, the initial condition, times e to the minus alpha times the number of years that have elapsed since 1667. Likewise, we'll be interested in wc of t, the number of words from Chaucer's time still in common usage. This has the same solution with 1667 being replaced by 1400. Most importantly, the alphas are assumed same because this is all English. Now, what is it that we are given? We are told that the number of words from Milton's time in common use today, let's say in 2012, is 80% of those originally available. Plugging in the solution to the differential equation for w sub m when t equals 2012 and then dividing by the initial condition gives us a single equation that has only alpha as an unknown. We can therefore solve for alpha, and we get a quantity that is about 6.5 times 10 to the negative 4. Now, if we use that alpha in our solution for w sub c of t, then what can we get? Well, our goal is to find the fraction of words from Chaucer's time that people in Shakespeare's time would have understood. That is, wc of 1600 divided by wc of 1400. Plugging in our solution to the differential equation for w sub c gives us an answer of e to the negative 200 alpha. Since we know alpha, we can compute it. It's about 0.88, meaning that about 88% of Chaucer's words would have been recognizable to Shakespeare's audience. Well, that's pretty cool, but is that actually true? Well, I don't think so. This simple model that we've written down ignores so many features of linguistics, such as the creation of new words, such as the evolution of words. Words are constantly changing their meaning, so that even though a word does not fall out of common usage, it's really a different word with an altogether different meaning. Lastly, there is whole-scale evolution of language. I'm speaking American English, which is in some respects very different than British English. If you look at, say, computer languages, you can see, even over short timescales, very rapid evolution in the language itself. This brings us to an important conclusion that even though our mathematics was perfectly accurate, a perfectly accurate solution is only as good as the model on which it's based. If you have a bad model, it doesn't matter how good your math is, you can't conclude truth. So with that in mind, let's talk about zombies. And we'll model the zombie apocalypse as follows. The rate of change of the infected population is proportional to the uninfected population. If we denote by U of t, the uninfected population, and Z of t, the infected population, then P, the net population size, is a constant. That is, U plus Z equals P. Our model says that dz dt, the rate of change of the infected population, is proportional to U. That is, P minus Z. That constant of proportionality we'll call R. Now, what is happening to du dt? Let's think about that. U is P minus Z. So differentiating gives us du dt equals dp dt minus dz dt. Now, dp dt we know is 0 since p is constant. And we know dz dt equals r times u. And so we see that our zombie model is really just the linear differential equation in disguise for the uninfected population. We know the solution, u of t, is the initial condition, u naught, times e to the minus rt. That means that the solution for the zombie population, z of t, is p minus u of t, that is p minus u naught, e to the minus rt. Unfortunately, as t goes to infinity, this means that everyone is a zombie. Now, before you dismiss this differential equation as being ridiculous for modeling zombies, consider it may also be used to model the spread of disease, or the spread of propaganda, or the adoption of new technology in a population. This simplistic equation is not rich enough to really model these complex phenomena, but it's a good first approximation. It's even better when applied to heat. Newton's law of heat transfer is essentially the same equation. It says the rate of change of temperature with respect to time is proportional to the difference in temperature with the ambient environment. So in our zombie equation, this constant of proportionality, r, was an infection rate, and p was a constant population size. In Newton's law of heat transfer, the constant is a thermal conductivity. How easy is it for heat to spread? And the constant A is an ambient temperature. Same equation, very different interpretations. That's one of the beauties of differential equations.
And so we see one simple differential equation gives rise to so many applications. But what happens if we change that differential equation? How will we determine the solution? What is it going to be good for? In our next lesson, we'll consider some other classes of ordinary differential equations, their solutions, and their applications.